Okay, so now I'll describe how the covariant entropy bound heroically resolves all these counterexamples, does not run into them. But before I do that, let me just give you a slightly more accurate version of the actual definition of the bound. What exactly are these Lightsheets? So here I now emphasize that this is really a completely local definition. So this line interval here is a surface element. I'm suppressing one dimension, one spatial dimension. Time goes up as before. So this is just some piece of surface. Any piece of surface has 4 null directions that go orthogonally away from it. Future, 1 to each side, and past, 1 to each side. And each of these null hypersurfaces, these are in general 2 plus, in our world, these would be 2 plus 1 dimensional null hypersurfaces, 2 spatial directions here, and 1 null direction like that. You can think of these null hypersurfaces as being generated, or being in the sense the sum of all the light rays that emanate orthogonally from this 2-dimensional surface. Notice that in space-time, if I talked about spatial lines that emanate orthogonally from some surface, that would not be a well-defined statement because they could point up and down more or less in time. And so in general, of course, it's true that you have to specify something of codimension 1 to specify a line that's orthogonal to it uniquely. But these surfaces, which are of codimension 2 in the space-time, nevertheless have unique orthogonal null directions just because the nullness is such a strong restriction. Okay, that the fact that it's neither space-like nor time-like gives you only these 4 possibilities. So then each of these 4 null hypersurfaces are made up basically out of all the light rays that come out of this initial surface B right here. Now let me look down on this. I'm not including time in this drawing. This is sort of projected onto a spatial slice, if you will, or it's just the actual slice of the light sheet. Okay, here's my initial surface. It has some area A. So here are the light rays coming out of it. And as you see in this example, these light rays are contracting. Again, this is a local statement. I can look at any geodesic and ask, are the neighboring geodesics spanning a larger infinitesimal area with this one as I go along, or a smaller one? Okay, and this is mathematically a quantity defined as the expansion. And you can find all the gory details in Walt's book. But it's defined at every point. I can ask, how are the neighboring light rays behaving? Are they coming closer or moving apart? And basically, it's just the statement. The expansion is the logarithmic derivative of this area element as a function of the affine parameter. Okay. So if this quantity theta is negative, then we have contraction, and then that means we're going off in a direction that is okay, that is generating a light sheet. Now these light rays will keep going, and eventually they'll start intersecting each other. And I was showing earlier, I don't know where this drawing went. Do I have it here somewhere? Yeah. So in the spherically symmetric case, of course, they would all intersect in one point, but it's not important that they do that. Infinitesimally, there will simply be a point when a light ray intersects a neighboring light ray. And that's where I have to stop. At a caustic, the expansion goes to -infinity, and then it comes out at +infinity, and it's positive after I go through the caustic, because clearly the cross-sectional area is now expanding. And so I don't need a separate condition for where to stop. It's the same condition that theta should not be positive. So it's really theta less than or equal to 0. There is, let me see if I talk about this. No. Okay. So far, I haven't used any energy conditions, but there is a pretty innocent-sounding energy condition called the null energy condition, which is sort of the weakest one of all the ones that are floating around, which basically is the statement that the energy density as seen by light rays is always non-negative. TAB, contracted with a null vector twice, is non-negative. That condition, if it does hold, ensures that there is no other way for a negative expansion to become positive other than by going through caustics. And it guarantees that these caustics are reached within a certain finite affine time. If your expansion is some finite negative value, then basically after an affine time of order the inverse that value, you must reach a caustic. That's called the focusing theorem. It's just a statement that mass focuses light rays, not anti-focuses light rays. So it's not possible, if the null energy condition is satisfied, for light rays to come together and then just kind of start moving apart again. But again, this doesn't really enter into this definition. Okay, so now a light sheet is defined to be a null hypersurface orthogonal to the surface that you picked, which is completely arbitrary, called B, which has B as its boundary and which has non-positive expansion everywhere on this 2+1 dimensional null hypersurface. Oh yeah, so here's the story about the caustic. Also, assuming the null energy condition, we are guaranteed that to start with, when I start out at the surface B, at least 2 of the 4 directions away from it are going to be okay initially. Okay. If I violate the null energy condition, then of course it's possible for B to be a local minimum of the area, in certain, at least in degenerate cases.
Your null hypersurface is supposed to be generated by geodesics?
Yeah. Yeah. So in general, a light sheet need not be technically a hypersurface, because it's possible for the light rays to non-locally intersect. For example, if I construct the light sheets from the walls of this room, yeah, it'll be built from geodesics. What I'm saying is that geodesics don't always generate a nice hypersurface. There can be self-intersections. So there can be cases where the geodesics say.
Hypersurface is not always made by geodesics. That's what I'm trying to say.
Yeah, but these are. And in fact, any null hypersurface is always ruled by geodesics. This is true only for null hypersurfaces.
You sure that's it?
Uh-huh. Yeah, this is somewhere in Hawking and Ellis. If at any point there were so what is the statement? The statement is that I can basically break it up into a sum of geodesics locally. And if that was not true, then I could find 2 points on this null hypersurface which are time-like related. So I'll try to find the proof for you. But this is special to null hypersurfaces. They're very rigid objects, and this helps with this formulation. Good. So we have to stop at any caustic in particular. That's the usual place where you have to stop when light rays locally intersect each other. So that's the definition of a light sheet, and then the statement of the covariant entropy bound is then very simple. All the non-trivial information is in the definition of the light sheet. What I want to emphasize is that the order in which you do things is sort of the opposite of what I did in the space-like entropy bound. So it's not just that I went to something that's now somehow null and not space-like. I don't start by picking the region in which I want to look at the entropy of matter and then somehow finding its boundary. You have to go the other way around. You pick an arbitrary surface, and then this will tell you what the region is in space-time that has something to do with the area of this surface, or whose entropy is bounded by the area of this surface. So you always start by picking this B, then you can construct your light sheets. For any light sheet, it's true that the entropy on it is less than the area. I just remembered that I got a question at the end of the last lecture, which was an important one that I should have maybe addressed in the lecture. So let me take a brief break to do that. We were talking about Bekenstein and his generalized second law, and how it looks like if you throw stuff into black holes, this second law is upheld. The black hole increases by more, the area increases by more than the entropy that you lose. That's great. But what about black hole evaporation? In black hole evaporation, the area of black holes decreases. So isn't the generalized second law violated in that case? And the answer is that it's not. And it's remarkable because Bekenstein, of course, didn't know about black hole evaporation when he first proposed this. But you can check, and I think Page was one of the first people who checked this, that when a black hole evaporates, the entropy in the Hawking radiation is more than enough, not by a huge factor, but by some factor of order 1, to compensate for the loss in area. So that's an example where things happen the other way around. Now you're trading black hole horizon entropy for matter entropy, but again, the generalized second law is upheld. So I just wanted to answer that question. It seemed like important enough to. Okay, so let's go back to this bound. Let's now work through some examples. Again, I want to emphasize you can pick any surface, no matter how it's shaped. It doesn't have to be closed. But of course, in practice, we'll often be interested in relatively simple spacetimes where we can actually compute the geometry, such as spherically symmetric spacetimes. And those spacetimes can be represented by Penrose diagrams where every sphere is represented by a point. Light rays travel at 45 degrees. And you use a conformal transformation to somehow map the infinite spacetime down to a finite size or to blow the neighborhood of singularities up to exhibit exactly what the causal structure of those singularities is. So Penrose diagrams are very useful here. And of course, since light rays travel at 45 degrees and spheres are represented by points, the 4 possible directions in which you could go away from a spherical surface are simply the legs of this x. Okay, and now I said that generically 2 of them are going to be allowed, unless the expansion is exactly 0 in one direction, in which case 2 opposite legs are going to be allowed. But usually the expansion is non-zero on the surface itself. So say if it's increasing this way, then it must be decreasing that way, assuming the null energy condition holds. If it's increasing this way, it must be decreasing that way. So then in the Penrose diagram, you would indicate a sphere of this type by such a wedge. You show the directions of the allowed light sheets. And this would be an example of what you might call a normal surface. The light sheets go towards the past and the future in the same direction. If I had a sphere in flat space, that would be the way that this would look. This is an example of a trapped surface. The allowed light sheets go towards the future, no matter which spatial side of the surface you choose. And this would be an anti-trapped surface. And these are the things you're going to see near singularities. If you have a future singularity, like in a collapse situation inside a black hole or in a crunching universe, you're going to see these kind of trapped surfaces appearing. You're only allowed to look at the future-directed light sheets. Anti-trapped, say near a Big Bang, a sufficiently large sphere will be anti-trapped. Okay, so now I want to come back to these examples that were counterexamples to the space-like entropy bound. Here we had an arbitrarily small two-sphere bounding an arbitrarily large spatial region and arbitrarily large entropy in a closed universe. To analyze this from the viewpoint of the covariant entropy bound, now I really have to do a space-time diagram. Okay, this is crucial. The light rays are traveling forward or backward in time, and that is going to make a big difference. So here is a Penrose diagram for a closed universe. Again, Big Bang, Big Crunch. On these poles, the points are really points, and anywhere in the interior of the diagram, they are spheres. So this 3-sphere here corresponds to a line interval running from the North Pole to the South Pole, where the 2-sphere size grows from 0 to some maximum and then shrinks down again. And the little 2-sphere that I drew corresponds to a point in this diagram that's very close out here to the North Pole, this blue point here. Okay? So this huge spatial region that is enclosed by this tiny 2-sphere would be the line interval reaching from this blue point out here to the South Pole in this diagram. Okay? That's all the matter that's being picked up on this space-like volume. Okay? But now, what are the allowed light sheets? Well, of course, if the 2-sphere is very small, then it's as if it was in flat space. Okay, no matter what the universe is doing at large distances. We don't care what the universe looks like when we draw a small 2-sphere into space. We know what happens to light rays that go orthogonally away from that small 2-sphere. If they go towards what you would call the inside, then the area shrinks. If they go towards the outside, it grows. So the allowed light sheets are clearly the ones that go towards the North Pole. And it doesn't matter whether they go towards the past or the future. And so they do not see all this stuff, the world lines of all these materials that are going through this part of space, this huge part of space. They only see the little polar cap that is enclosed by what an ordinary person would call the inside of this two-sphere. Okay. And so now, as I take the two-sphere area to 0, the region that the amount of entropy on the light sheets also goes to 0, because the light sheets are basically, they're seeing whatever is on the inside of this two-sphere. Now, I'm not going to go through an explicit calculation for a specific universe with specific matter content to show you that in detail the entropy bound is quantitatively satisfied. That calculation would be very similar to the one that we did for the ball of radiation, say, if this was a radiation-dominated universe. But my point here is only to show that the obvious violation of the space-like entropy bound is not present here. It evades this obvious problem that we could see without doing any calculation. Okay. The next example was a flat Friedmann-Robson-Walker universe like the one that we appear to live in. So that's the Penrose diagram for that. In that case, there's just a big bang. There's no future singularity. And there is only one edge where the spheres degenerate to a point, the origin, r equals 0. And a flat R3 slice would be a line that runs from some point here down into that corner. That would be a constant time slice in the usual FRW time. Okay, and our trick was to use very large regions. So I pick a sphere out here, a very large sphere. And in the space-like entropy bound, I said, well, that encloses all of this stuff between this point out here and r equals 0. It encloses a three-dimensional ball of stuff. And I can make the entropy in that ball grow like r cubed. The area grows like r squared, because we're talking about Euclidean geometry. And I can violate the space-like entropy bound. But if I make the sphere very large so that I run into this problem in the first place, then I'm certainly in this anti-trapped region. All the spheres in this triangle here are anti-trapped. Only past-directed light sheets are allowed. Okay. And so these light sheets don't see the same thing that the space-like entropy bound saw. They don't get, if I say really pick this particular surface here that's at the tip of this wedge, and I follow, say, this light sheet, I don't get to see the world lines of all matter particles which travel up like this all the way to r equals 0. I get truncated by the Big Bang. Okay. And now if I move the surface out to larger and larger area, larger and larger radius, the width, the co-moving width that these light rays see is actually essentially constant. And so I'm making both the area and the volume that they see grow at the same rate. It's a shell that is being captured. It's a shell of material that's being captured by the light sheet, not a whole solid ball interior of this two-sphere. Is this clear? So this is the kind of conspiracy that I was talking about. You know, well, you have to solve, and now the singularity comes to the rescue and cuts off your light sheet and prevents you from running into trouble. But why does this always happen? I don't know. The collapsing star. This is a Penrose diagram for a collapsing star. I've started it at the time when the star just crosses its event horizon, so I could have followed this back. And of course, in the Penrose diagram, actual sizes are distorted. What's happening here is this is the origin again, r equals 0. This is the surface of the star, some finite radius, but the actual area goes to 0 as I move up in time and approach the singularity. The area is actually equal to 0 up here. Okay. Our trick there was to say, well, this star has some entropy. I don't care what it is. The space-like entropy bound says that this entropy should be bounded by the area of the surface of the star, which I can make arbitrarily small at late times, so clearly I have a problem. Okay, but if I pick one of those small areas at late times close to the singularity, they are anti-trapped inside a black hole. Sufficiently large spheres, they're trapped. They're trapped, so only future-directed light sheets are allowed, and the future-directed light sheets again get truncated. This one here is not very interesting because it doesn't see any matter at all. And the one that goes to the left is truncated by the singularity. as I make the area arbitrarily small, the light sheet sees a thinner and thinner shell on the surface of the star. So the entropy that it sees also goes to 0. Again, you need to do a quantitative calculation to show that it goes to 0 fast enough for there not to be a violation. And I'll leave that as an exercise for the afternoon. And finally, there was the case of the nearly null boundaries, the objection to the space-like entropy bound that really you can surround any object with a surface area that's arbitrarily small by kind of wiggling it up and down in time and making it have null pieces. But if this line here is almost null, let's stay in this really 2 plus 1 dimensional picture for simplicity. So let's imagine the world is 2 plus 1 dimensional. The area is really the length of this line, which is very, very short because this is nearly a light ray. The distance from here to here is nearly 0. Well, what do the orthogonal light rays look like? Well, the light rays orthogonal to this edge here would go straight, they would respect what we would ordinarily call the dimensions of the room, the coordinate system that's useful. If this is, the x direction, the light rays would go exactly in the y direction. But the light rays that are orthogonal to this line do not go in the y direction. They go off to the side. That's what it takes to be orthogonal to this green line. And so if I look down on this and ask, well, what part of the system do they sweep out? What part do they see? Well, it's a triangular region like this. Okay? And then there are light rays coming from the other 3 edges, and they see similar regions. And so in the limit where I make these green lines exactly null, the size of the regions that are actually seen by the light rays in the interior of the system goes to 0. Okay, and so we no longer have a situation where I can take the area to 0 while leaving the entropy fixed, which was the problem before. Yes?
This boundary that we're taking the area of, do we need to have the light sheets, the geometry of the light sheets worked out before we can calculate what the area of this boundary is?
No. You can specify a 2-dimensional spatial surface in space-time and use the metric, which I assume you have, to compute its area. Okay, and you could have always done that with or without light sheets. And then it's a separate and more elaborate step to construct the light rays that go orthogonally away from that surface.
So how do we get the area from the light sheets? How is that different?
Well, so the important thing here is to do things in the right order. So my rule is that you have to start by picking a 2-dimensional surface. And you really can pick any one that you like. And as soon as you've picked that, the first thing you want to do is compute its area. Okay, and then the next step is to construct the light sheets away from it. And the claim is that they will see less entropy than that area. There are, of course, situations, and I'll get to them, where one would like to do a kind of inverse construction. So, for example, a passed light cone of a point is, of course, a light sheet off of any cross-sectional surface that you can pick in that passed light cone. If it's in Minkowski space, say, then you pick any sphere somewhere down on the light cone, and then, well, the direction up towards the tip of the light cone is an allowed light sheet. If you're in a Big Bang cosmology, say you're like where we are right now, you'll get our passed light cone, as I discussed in the previous lecture. There, you have this funny situation that the area grows towards the past and then has to start shrinking again as you approach the big crunch. So if I don't draw it in a Penrose diagram, it would kind of look like this. And now it gets more interesting, because now there's a sort of preferred surface, which is the one of maximal area, the apparent horizon, which has the property that two light sheets in opposite directions are allowed, which if you put them together recreate this entire passed light cone. And so that's a surface that is of particular interest because, for example, it allows you to answer the question of what the maximum entropy in our passed light cone is. If you pick any other surface, then it will only allow you to bound the entropy, well, either between it and the Big Bang, if it's an anti-trap surface, or between it and us right now, but not the part outside of it that also belongs to our passed light cone. But this surface on the apparent horizon is the one that's really interesting. And so that's the surface that you would perhaps call the holographic screen in a space-time like that. It's where you would want to put your information in order to really describe everything. So I'll come back to that in a little while. Other questions? Okay. So how am I doing with time? I have until 3 or something, or no, 3:30? 3:30, okay. Good. So let me say a few words about ADS-CFT. And, well, really, what I want to come back to now is this statement at the beginning. That you know, we have this thing, we have this entropy bound. It's very general, and we don't know why it works. Okay, and so it'd be nice to have a theory which makes it obvious from the start that it couldn't have been any other way. A theory that makes it obvious that, for example, the size of the Hilbert space that you're using in order to describe all the physics that's on some particular set of light sheets is no larger than the area that those light sheets start from. Okay, something which just makes it clear that there is not more information in the theory to start with than the maximum entropy that these bounds claim. Okay, that would be nice. That would make it clear why these bounds hold. And the only example that we have of such a theory is, well, precisely the only example I think we have of a full non-perturbative definition of quantum gravity, and that is string theory in asymptotically anti-de Sitter space, which is fully defined by a conformal field theory that you can think of, if you like, as living on the boundary. So let's look at this example and see what it can teach us and perhaps what it hasn't taught us yet. First of all, is this something that makes the holographic principle manifest? Is this something that explains why these entropy bounds hold? And the answer is, well, yes, for some surfaces. The covariant entropy bound is very general, and it allows you to pick arbitrary surfaces in the interior of ADS and construct their light sheets and make claims about their entropy. But if I pick a sphere that's sufficiently larger than about 1 ADS radius, then I have a way of using ADS-CFT to check that the number of degrees of freedom in the theory is really no larger. The degrees of freedom that describe what's on the light sheet of that sphere is no larger than the area, the number of binary degrees of freedom, so the amount of information. So how does that work? Well, if I pick, say, this green sphere at an instant of time, I construct a light sheet that sees, well, basically you have to use information about the geometry of ADS, but the allowed light sheets go towards the center. They go all the way towards the center. So the statement is, the covariant bound tells you that this area is larger than the entropy of everything that you could have put into in the interior of that surface. And actually, the thing that saturates this bound would be to put a very large black hole that just fills up this green region. But anyway, that's the statement. Now, the CFT has, of course, an infinite dimensional Hilbert space. It has degrees of freedom at arbitrarily short distance scales. But fortunately, there is a cutoff version of ADS-CFT that was clarified by Susskind and Witten, where you ask, okay, well, what if I don't want to describe all of anti-de Sitter space all the way out to the boundary? What if I'm content with just asking about stuff that happens in this green region that has a finite distance, infrared, if you will, cut off? I only want to describe stuff that happens in there. Now, in exchange, I should be able to throw out some of the states of the CFT. And what turns out to be the right thing to do at least approximately, is to impose a UV cutoff on the CFT. And the relation between the IR cutoff and the UV cutoff is pretty simple. In fact, it can be captured by just using, again, light rays. If you pick a UV cutoff that corresponds to some scale delta on the boundary, and you ask, well, let me consider a light cone on the boundary that grows out to that scale delta. And let me ask how far that light cone has propagated into the bulk. Well, on the boundary, by imposing this UV cutoff, I'm throwing away information about stuff that's in the interior of the light cone, things that are smaller than the size of this light cone. I can't describe those. And so there should be anything that I can do. I should have two equivalent ways of talking about it. One is to just talk about the CFT on the boundary. Another is to say that I'm sending a probe into the bulk. Okay? And now the statement is that until the probe gets deep enough into the bulk so that the boundary light cone becomes larger than delta, I shouldn't be able to describe that part of the bulk. Okay, so all I need to do to figure out where this bulk cutoff is that corresponds to a boundary cutoff, UV cutoff delta, is to ask how far light rays travel into the bulk. That's just a causality argument. By the time that they've spread out to size delta on the boundary, and then throw out that entire region of the bulk that is seen by those light rays that have only seen this sort of outer shell of the bulk. Okay, so you get a formula. And this formula tells you that the larger you make this UV cutoff scale, in other words, the lower energy you make the UV cutoff, the less of the bulk you describe clearly. You describe what's in the interior of this green region. Okay, so when you do again, for the math, you can look at the Susskind-Witten paper, or you can look at my review. But the relation is such that, well, for any delta, you can compute two things. Okay, you can compute how large is the Hilbert space of the boundary theory if you assume that you discretize the boundary theory on this scale, and that in every cell you basically have an order 1 number of states per field theory degree of freedom. Okay, that gives you an estimate for the size of the Hilbert space of the boundary theory. Okay. The other thing you can do is compute the area of the associated infrared cutoff surface in the bulk. Okay. And it turns out that e to this area is equal to the Hilbert space that you estimated on the boundary theory. In other words, the Hilbert space of the boundary theory is just large enough that you have all the states that the covariant entropy bound allows for these green regions, but no more. There are not more degrees of freedom in the fundamental theory that describes this to start with. There just isn't more stuff there that could make you violate this bound.
Is this a statement of how things scale or numerical factors?
It's up to factors of order 1. Yeah. On both sides of the calculation, there are some uncertainties of order 1. Okay, so this is great. Now, it's not perfect. It's not perfect because, for example, we don't understand how the covariant entropy bound is made manifest by ADS-CFT for spheres that are smaller than 1 ADS radius. Okay, what happens in that case is that basically, if you consider smaller and smaller spheres, it corresponds to considering a longer and longer UV cutoff length scale on the boundary. And by the time you get to 1 ADS radius, a sphere of size 1 ADS radius in the bulk, the corresponding UV cutoff is basically the size of the whole boundary. Okay, so at this point, you basically reduce the boundary theory to sort of matrix quantum mechanics, and there's nothing more you can do to it in terms of a length scale cutoff that would explain why the number of degrees of freedom keep getting smaller as you consider even smaller regions in the bulk. So the way that the relevant degrees of freedom for a small region, small compared to the ADS scale, is encoded in this large matrix on the boundary is to a large degree still a mystery. And we don't have an explicit way of extracting that part of the Hilbert space of the boundary theory and checking that it has an area worth of degrees of freedom in it.
For
Yeah.
You already said, these things coincide with the Bekenstein bound.
So the Bekenstein bound is strictly speaking this one, right? Which I haven't been talking about for quite some time, and which has not made an appearance here. That's the one that doesn't involve area but mass times radius. And it doesn't have G Newton in it, for example. So the story of how that fits into this is a subtle one and somewhat unresolved. I can say a little bit about that if you like. Let me first maybe stay with the theme of area. Another question, yeah.
Maybe this is away from the theme of area. If you wanted to do this in higher dimensions and you took some sort of ball, is the construction just a natural generalization? Is where you split it up into, these two
Yeah.
different areas?
That's right. Thanks for asking that. Yeah. So the general statement is by an area, I mean a spatial surface of codimension 1 plus 1 in the spacetime. So if the spacetime has d spacetime dimensions, then it's a spatial surface of dimension d minus 2. Other questions? Good. So, so let's talk briefly about other spacetimes. I mean, the question is, how much does this teach us about how holography is going to work when you're not in anti-de Sitter space? Okay. And let me start with the good news. Okay. The good news is that the world is always a hologram in the following sense. You might have thought that this idea that you can specify all the data about what's going on in the world on its boundary at a density of 1 per Planck area or something clearly doesn't make any sense in spacetimes that don't have a boundary. And the best example of such a spacetime is a closed universe that starts at a Big Bang, ends in a Big Crunch. Neither spatially nor temporally is there a good boundary, which in some sense is large and where you could imagine storing information. So what can we do? Well, we can use this kind of construction that I already discussed. Suppose that you're here on the north pole of this 3-sphere. Of course, no matter where you are on the 3-sphere, you can call it the north pole. And you look at your past light cone. This is your past light cone, this line here. And what you can see from these wedges is, well, for a while the area is going to be increasing, and then here it reaches a maximum, and then it starts decreasing. Every sphere in here has decreasing area towards the past. And so if you choose this maximum area as your initial surface, then it is true that the total entropy on this entire past light cone is no larger than A over 2. One A over 4 for this side and another A over 4 for that side. Okay, I'm not sure how important this factor of 2 is here, but my point is just that if you chose any other cross-section of this past light cone, you would not be able to make a statement about the entropy on the entire past light cone that has anything to do with that area. Right, if you pick this area, well, you can say that it bounds the entropy on the little region between that area and r equals 0. And if you pick, say, this sphere here, well, its area bounds the entropy in the region between that sphere and the place where the light reaches the Big Bang. Okay. Only if you pick this sphere can you say something about, well, this area bounds the entropy on the entire null slice. Think of these past light, so now stack a bunch of past light cones on top of each other. This is your past light cone tomorrow. This is the past light cone the day after tomorrow. You can just repeat this procedure for each one of them. Okay, and for each one of them, it's going to be true, according to this bound at least, that the total Hilbert space that you'll ever need in quantum gravity to describe what's going on these slices cannot be larger than the maximum area on them, the area on this apparent horizon. Okay, so you can think of the entire spacetime as being foliated, just like you would think of it as being sliced into space-like slices. Think of it as being sliced into null slices instead. And if you do it that way, then you can always find a good holographic screen in the sense that you can find an embedded, in this case, hypersurface, which has the property that its areas bound the entropy on slices which really foliate the entire space-time. Okay, or in other words, you can take all the information at every slice of this kind of null time and project it at a density no greater than 1 bit per Planck area onto this sequence of screens. So that's a little bit similar to what we were able to do in ADS CFT. We can take all the information in the screen region and really at every time, in this case, we could really do it at every instant of time, project it onto this cutoff boundary again at a density no more than 1 bit per Planck area. Okay, so that's where the similarities unfortunately end. So the world is always a hologram in this sense. You always have this property that you can project in this way. But except in ADS, and even there I think only in special cases, we don't know very well how this encoding works. And there are many things that happen in ADS that seem, in hindsight at least, very fortuitous, and that those properties are not shared in arbitrary spacetimes. In anti-de Sitter space, the theory that became the exact definition of non-perturbative string theory in anti-de Sitter space, that theory is an ordinary, perfectly well-defined quantum field theory, conformal field theory. It's unitary. You can put it on a computer. You know in principle how to compute anything you want with it. And this is possible because the holographic screens have, first of all, are arranged in a time-like sequence. So the time variable in the holographic theory is essentially the same as in the bulk. And I can at least choose the holographic screens to have constant area. And so the number of degrees of freedom in the theory is preserved. And I don't have a confusion about, if the number of degrees of freedom changes, then I don't have unitarity. In a general space-time, those things will not happen. Okay, they will not happen. Here's one. Well, let me go back to the closed universe first. There you can see it very clearly. Down here, the holographic screen has 0 area. The area grows for a while. Here is the place where the holographic screen coincides with the equatorial 2-sphere of the 3-sphere. And this is also happening at the time when the universe is expanded to maximum size. So here the spheres are actually, this is very large. This is the largest sphere in the entire space-time. And then it starts shrinking again until it has 0 area. And so what to make of that, I have no idea. Okay. It seems to say that the number of degrees of freedom, at least that are being used or that are being accessed, is changing as a function of time. In particular, it can even decrease. That doesn't seem to bode well for a description in terms of a simple unitary field theory, unless you figure out a way to change the cutoffs in an interesting manner. And other examples of this type, say if you have a black hole, what does the holographic screen look like in that case? Well, first of all, there's a huge redundancy, or if you want, a gauge redundancy of how to construct holographic screens. Because in a general space-time, what I did is I chose a particular world line and I looked at all the past light cones down from points on that world line, and then I looked for maximum areas in each one of these past light cones. I put them all together, I get my holographic screen. But of course, the surface that I get in this way depends on which null foliation I choose for the space-time. And there are many possible choices. Here again, for example, I could use future light cones, or I could use past light cones. Okay? This is what happens if I choose past light cones. They have their maximal area at the past infinity. So this is a black hole in asymptotically flat space. This is past and future null infinity. This is the singularity. This is the horizon. Here's r equals 0. The past light cones in such a spacetime, no matter where they start, have the property that their area just keeps on increasing forever. You're just getting far away from the black hole. It's like flat space. Of course, they keep increasing. The future light cones, not so. If they don't fall into the black hole, then they increase forever. But if you're inside the black hole, then the future light cones increase up to a certain point. You can see that here from the wedges. So areas increase towards the tip of the wedge. and then you reach an apparent horizon inside the black hole, and then the area starts decreasing, as it must, because you're approaching a future singularity where everything crunches down. So in that case, you get a holographic screen that kind of looks like this. There's a piece inside the black hole, which is partly time-like, partly space-like. Then there's a disconnected piece outside the black hole, which consists of future null infinity. It's a mess. Okay, it's a real mess. The statement remains true that all the entropy that you can fit on any one of these light cones is no larger than whatever the maximum area is along that future light cone. That's true both inside and outside the black hole. But these thick black lines here do not look like a happy home for a nice theory. Not even connected, yeah. Yeah, so I have a little bit of time left, but let me actually stop for some questions at this point.
So in the ADS-CFT example, then would you say that depending on whether you did this usual light-like projection that you constructed, or if you sort of did the space-like projection version, that you should get two different forms for the dual theory?
Good, yeah. So I wanted to come to this is perfect. I wanted to briefly discuss this anyway. Can you see this okay, or is it, yeah? If your space-time is sufficiently nice, we would like to understand why this space-like entropy bound does in fact work for many examples, but not all. Okay, so is there some way that we can understand that? And suppose you have a sphere like this. Okay, it doesn't have to be a sphere, but now I'm going to insist, first of all, that you choose a closed surface. Because clearly the space-like version of entropy bounds, there's no hope of recovering that if you don't have a closed surface. You didn't even know what you mean by the interior of a surface if it's not closed in the space-like sense. So let's start with a closed surface. And now let's look at where the light sheets are. And now suppose that there exists a future-directed light sheet, which is not, for example, cut off by some singularity in some horrible way, because it happened to be deep inside a black hole, but which happily continues on until it basically closes off, in the sense that there exist no world lines that pass through this space-like volume that don't also pass through the light sheet. Okay? If that's true, then clearly the entropy in this space-like volume here, well, by the ordinary second law, has to be less than the entropy on this light sheet, because everything, all the matter that passed through this slice, so here's a matter system, all the matter that gets counted in this entropy on this volume also gets counted on this light sheet. There's no escape path where it could get through without counting on the light sheet. Okay, so this is going to be true, and then by the covariant entropy bound, that's less than A over 4, where this is the area. Okay, and so in this situation, I'm able to recover a space-like entropy bound. But now I understand the conditions under which that bound is valid. It's valid if there exists a future-directed light sheet, and if it's complete, if it closes off. Now, anti-de Sitter space, in most cases, is a situation where that does happen. So if I have anti-de Sitter space and I don't have something in there with a huge amount of gravitational back reaction, then it certainly is true that I can pick any area here out near the boundary or at the actual boundary, and it'll be true that a future-directed ingoing light sheet exists and closes off. Okay, and so I have a certain right to say that I can, if I want, claim that there is a correspondence time slice by time slice. I actually think that there's an ambiguity there. I mean, it doesn't matter if I say that I don't think it can possibly matter if I have a state in the conformal field theory that's defined on this particular time slice, whether it corresponds to this slice in the bulk or that one, I think it's up to you to choose that, but you can certainly choose to work in a gauge where you think of it in that way. Things get more interesting when you start having black holes in anti-de Sitter space. So let me now draw a proper Penrose diagram. So here's R equals 0. Here's the black hole singularity. And the kind of light sheet that I drew over there would be one like this. This black hole was formed by some star here, but down here the geometry was still totally harmless, essentially empty ADS. I get these future-directed light sheets that close off. The light sheets off of this sphere on the boundary does not close off. So if I think of this as a regulated boundary, has finite area, at this point, at least I don't have an argument that the entropy in this spatial volume has to be less than this area. Yeah.
Could you comment briefly on the Linde's gravity and entropic forces and whether that has any light shed on it, or whether that type of gravity
Well,
sheds any light on it?
So I think that, what's the message here? The message is that you would like to find a theory, a quantum theory of gravity and matter, in which it is true that classical spacetime, in the limit where you have classical spacetime emerging, that emerges in such a way that the number of degrees of freedom that are used to describe what happens on certain light sheets is not larger than the area of their boundary. So I think this is something that we probably all agree on, that's something desirable that we should look for. Up to a certain point, I think ADS-CFT makes this very explicit in this particular example, but we would like something more general. And I don't understand what Eric is saying beyond that point. I don't understand the more detailed arguments in his paper. I was not able to make a coherent story out of them, so I shouldn't comment on that. But there's there was an interesting attempt several years earlier, by Bob Jacobson, in which he tried to recover general relativity as some sort of thermodynamic limit by considering little area elements that are Rindler horizons, and demanding that for any such area element, no matter where it is and how you orient it in the space-time, the first law of black hole mechanics holds, and that in some way allows you to recover Einstein's equations. But it's one of those tantalizing papers that never went anywhere. It seems like there's something missing. It's not clear to me how to go from that to understanding how the geometry really emerges from an underlying quantum gravity theory. Yeah.
When you're computing areas in this so you start with circles and you compute an area, for example, you said the metric is fixed and known. So
Yeah.
you have to worry about gravitons.
Well, classical gravitons are not really a problem. I mean, I think the real problem is that in situations like a closed universe, in any situation where the holographic screen is in the interior of the space-time, it's clear that what you mean by this area and what you mean by this screen is not arbitrarily precisely defined. And so, and this is, it's not really a huge surprise. I mean, I don't think anybody thought that we would ever find completely exact observables and an arbitrarily precise description for something like a closed recollapsing universe. But to me, it signals that there's a lot that we don't know about quantum gravity that couldn't possibly be captured by ADS-CFT. I think that there are still big pieces out there to be discovered that have to do with situations where no exact observables exist, where gravity is dominant, where you're in the neighborhood of singularities. And I think that what's interesting is that these entropy bounds they're a very limited statement. They don't tell you what the theory is, whose entropy you're actually talking about here. They just tell you something about a relation between quantum states and geometry that is true in a certain classical limit of classical space-time geometry. And so they constrain to some extent the quantum gravity theory that could possibly lead to that geometry. And the nice thing about them, so that makes them somewhat limited, of course, but the nice thing about them is that they're so general, that they work in those situations where string theory has so far at least not been very explicit about how to do quantum gravity, such as in cosmological regions. And so I feel that to some extent it's perhaps a complementary tool. String theory is very, very good at making precise statements. And the problem is that these problems are associated with situations where you have no hope of making precise statements. And the question is, how far can you go and still making progress on describing quantum gravity there? Well, if you want to really speculate, for example, I think it's not obvious. So far, we have not had to give up unitarity. String theory is manifest. Every description we have is unitary. ADS-CFT is clearly a well-defined unitary quantum field theory. We haven't had to give up quantum mechanics. And I think it's an open question to which extent that's going to remain true when we understand how to describe cosmology better. Perhaps the fact that we haven't had to do this so far is a sign that we'll never have to do it. But perhaps the reason that we haven't been so successful with cosmology is a sign that we might have to do this. I don't know. More questions? I have until what, 3:30? Yeah, good. Tell me.
So what happens in situations where you have NEC violation?
Where I have what violation?
The non-energy condition.
Clearly, if you allow me to invent arbitrarily 6 types of matter, I can violate the covariant entropy bound. Because what the covariant entropy bound relies on is that matter always focuses light rays enough that by the time you've sort of reached your allowed amount of entropy, the light sheet gets terminated by caustics. The focusing, however, is done by the energy density of the matter. And so there is some conspiratorial relation between the energy density and the entropy density, roughly speaking, which is not rooted in any fundamental principle that we know. It just happens to be true, apparently, with a matter with types of matter that we're familiar with. If you allow me to violate energy conditions arbitrarily, then I could invent forms of matter whose role it would be, for example, just to cancel out the energy of the entropic matter that sits on my light sheet and make the total energy density 0. Of course, that would have to have negative energy in some horrible way. And then I could violate the bound. The question is, I think the interesting question is, I'm not worried about that because we don't see such matter, but we do, of course, see violations, local violations of the null energy condition in quantum field theory. This thing is not enshrined in, and I don't know of any example where those violations allow you to violate the entropy bound. And the entropy bound is not formulated in a way that explicitly makes reference to the null energy condition. And so that's all I can say about it. So in other words, I don't know of a way of violating the entropy bound with physical matter that we think actually exists, even though we know that this physical matter that actually exists allows you to violate the null energy condition a little bit for a certain amount of time in certain regions of space. So that type of violation does not seem to be something that easily allows you to construct counterexamples. But I would be interested to.
I would think that the situations such as Bekenstein
pockets of?
Where the universe starts expanding faster,
Yeah.
that you will have violations of the ADC, of the
Well, I don't see how eternal inflation is special. I mean, the fact that you have inflation just violates the strong energy condition. So I don't see how the null energy condition is more or less violated than you could violate it in the lab. Oh, by uptunneling. Yeah. That's a situation, though, where, I mean, uptunneling is a situation where the semi-classical gravity approximation also breaks down. So it's not really a regime that I can control very well here. The geometry as a whole changes very dramatically on a large scale. Nima.
There's some distinction between, well, there is some way of characterizing the way in which Casimir energies or general negative energies can allow negative energies in filter, even though they violate the null energy condition, they do satisfy this integrated version of the null.
Yeah, right.
Now, in these proofs of using entropy flows and rate generator and all those wonderful proofs of the covariant entropy bound.
Yeah, they're not proofs. They are not proofs in the sense that they simply identify sufficient conditions.
Okay, right.
But those conditions themselves are not a given in physics.
I understand, but what I was wondering is, those genuinely use this local version of the null energy condition? Is there any,
Yes, they do. They do. I mean, they're roughly of the form that the entropy density is times something is less than T mu nu contracted with two null vectors, and this is so they're stronger than the local version of the null energy condition. In the sense that this number here could be positive. The null energy condition would just be. Well, then they're strong in the sense that, yeah, if you think of the energy density as being the thing that's given, then you're requiring that the entropy density is given. You're requiring that the energy density is in some sense larger than that. And if the entropy density is 0, you're therefore requiring that the energy density is larger than that non-zero number. But yeah, it's completely local. And that's the basic. So just to give the background for Nima's question, soon after the covariant entropy bound appeared, Flanagan, Meroff, and Wald published what they call the proof of it, and it is a very nice argument. They basically save you from checking a very large class of examples, including explicitly checking every single one of these examples that I gave you, by saying, well, if I'm in a situation where I can treat entropy as in a fluid approximation, I can talk about entropy density that I get to integrate over the light sheet. And if that entropy density satisfies a certain local inequality between entropy density and energy density, then I can prove that entropy always costs enough to focus the light rays and terminate the light sheet before they see too much entropy. And that's very nice and it's very useful, but of course it's not a proof in a real sense because even the very sort of notion of a fluid approximation to entropy density is not fundamentally correct. It's very useful in cosmology and so on, but if you're talking about distances that are smaller than the characteristic wavelength that encodes of the quanta, they encode the entropy, it doesn't make any sense. And even in the regime where it is correct, there's no, I mean, where the fluid approximation is a good approximation, there's no fundamental reason why the inequalities that they had to assume. And by the way, I wrote a very similar paper with Flanagan and Meroff afterwards that simplified these assumptions. But there's no fundamental reason why these assumptions have to hold. There's some reasons why they have to hold given what we know about the kind of matter that we see in our universe on sufficiently large scales and so on. But it's not a proof. It's not something that really explains why things are the way they are. Other questions? So if there are no more questions, then I would actually like to have the screen removed, because then I want to talk a little bit more about the Bekenstein bound that I said I was going to come back to. And I don't know if somebody's there that could do that. Otherwise, I'll just work with a small blackboard. That's fine too. Some light would be good. Okay, so thank you. So this was this amazing bound that Bekenstein obtained by imagining that, you have a big black hole here. You have your matter system that has entropy S in it, and which has radius R. And you hang it on a string, and you lower it slowly down towards this black hole, and then you drop it in at the end when it just starts touching the horizon. You compute by how much does the area of the black hole increase when you do this. Okay, and it increases by this amount. And the funny thing is that G Newton drops out. So this is a statement where in the end you can forget about gravity. So this bound seems really attractive because, at least for the weakly gravitating systems for which you can do this experiment, it's much, much tighter than the holographic bound, which is this one here. Right? Because M is much, much less than R over G for such systems. So it seems like it gives you much more interesting information. But it remains tricky to understand. Well, let me say two things about this bound. First of all, what does it have to do with the covariant entropy bound? It seems at first like it's hopeless to try to recover something that is stronger than a bound in terms of area from the covariant entropy bound. So how can my statement from earlier on be true that somehow the covariant entropy bound should be thought of as the primary thing and all these other things as limits that hold in certain cases? That question, I think, has been answered. Okay. The harder question is what sort of sense to make out of a bound like this. The problem is that let me start with the first question. So how does this bound come out of the covariant entropy bound? Well, for that I first have to tell you something else, which is how does the second law of the generalized second law of thermodynamics come out of the covariant entropy bound? Well, here's a star, it has entropy S, and it collapses to make a black hole. So here it crosses its own horizon. The question is, and here is the black hole horizon at a late time when everything has settled down. It has some area A. Okay, the question is S always guaranteed to be less than A? Well, the generalized second law says that, but we don't have to say that anymore. We can simply use the covariant entropy bound. Let's pick this as our initial surface. Okay. All the spheres in this region, they're far away from the black hole. They behave like spheres should in flat space. In other words, the inside directions are the ones towards r equals 0. Okay. The spheres in this region here are trapped. So the allowed light sheet directions go towards the future. Okay. This sphere here on the horizon itself is marginally trapped. That means it has 3 allowed light sheet directions. You get to pick the best of both sides. Okay. The one that I'm going to be interested in is this one. The one towards r equals 0 going towards the past. This is a light sheet. Okay. And the entropy on this light sheet by the covariant entropy bound is less than A. So the generalized second law immediately follows. Okay. That's great. But I cheated a little bit in claiming victory, because the generalized second law is a much more general statement. It also has to hold true if I already have a black hole and I add some matter to it. Okay, so here I make the black hole maybe with a star or whatever. At this point, everything is settled down. I have some horizon area, the black hole sitting there with this area, and wonderful, that area is bigger than the entropy 1 of that star that I threw in, A1. Okay. Now, I wait for a long time, and then I throw another object into the black hole with entropy S2. Okay. Now, actually, let me call this A prime and A. So A prime is greater than S1. But is A greater than S1? So the other thing that I can immediately show is, by using exactly the same argument, use this as my initial area, use this light sheet, it follows. So this shows that, and forget about the factor of 4, okay? I'm just being schematic here. A prime is greater than S1. Okay, this light sheet tells you that A is greater than S1 plus S2. But the generalized second law, in this case, allows a stronger statement. The generalized second law would say that the difference in the black hole area before and after I threw in the second system should be greater than the entropy of that second system. Okay? And these two things, which I'm able to derive from the covariant entropy bound, do not imply this one, obviously, since I can't subtract inequalities. Okay. And this motivated, that's the other interesting thing that Flanagan, Maroff, and Wald did in the same paper, actually. This motivated them to propose a generalization of the covariant entropy bound. So in the covariant entropy bound, what we've been doing so far is to say, well, if you have your light sheet, it goes off like this. You just make it as large as you can. You have to stop when you get to a caustic. Okay? But if you stop sooner, well, that's your tough luck. I mean, then if you stop already here and you don't include this part of the light sheet, well, then there's some entropy, there's some matter that these light rays are not picking up. And so your right-hand side is fixed, A, and you're just making the left-hand side smaller than you absolutely needed to. So you're not testing the bound as hard as you could have. Okay. But they said, well, let's do something else. If I stop early, so here's my initial area. Cross-sectional area gets smaller and smaller and smaller. If I go all the way to the caustic, the cross-sectional area is 0. But if I stop early, then I still have some finite cross-sectional area. Let's call it A prime. And so maybe I can tighten the bound. If I stop earlier, maybe I get to say that the entropy has to be less than the difference between these two areas. Clearly, that limits to the ordinary covariant entropy bound in the limit where I extend the light sheet maximally all the way to the caustics. But it strengthens the bound in the situations where I don't. And that's precisely the situation that I'm interested in here. I'm interested in such a partial light sheet that runs from here to there. Okay. And that's a very attractive proposition, because it now means that if I accept this stronger version of the covariant entropy bound, then I can really derive the generalized second law in all possible processes, even when I throw something into an existing black hole. The other reason why this is an interesting proposition is that it allows you to, this took a few years to somehow filter out, but it also allows you to derive the Bekenstein bound. Okay, and the way you do it is you just have to set it up cleverly. So here's your matter system. Okay, it has radius r, and it has mass m. Now, to get a really tight bound, what you want is you want to consider an initial surface, which has the property that initially the light rays are have zero expansion away from it. It's just barely an allowed light sheet. Why? Well, take flat space, okay? If I pick a plane in flat space, like the walls of this room, okay, and I look at orthogonal light rays away from it, these light rays will keep on going forever. And that's fine. They only keep on going forever if they don't encounter any matter that will focus them. Okay? But that's sort of the borderline case, right? On the other hand, if I start with a spherical surface in flat space, and I look at the allowed light rays, they don't keep on going forever. I have to terminate the light sheet when they meet in the center. So here I've sort of wasted expansion. I've already started with negative expansion, and then the focusing theorem ensures that the light rays will focus, the light sheet will have finite extent, even though there's actually no matter around. So I get a gap, right? Entropy is 0, the area is large. It's still true, but it's not very tight. Okay. So if I want to get a tight bound, I want to start with the situation where the light rays have initially 0 expansion. Okay. So think of X-raying the object. Okay. Or another good analogy to what's happening here is like the experiment whereby you measure the focusing of light by the sun, the bending of light by the sun. You have an object here which has a certain mass and a certain radius, and what it's going to do is it's going to bend those light rays, and an image appears. So I could, of course, now wait until the light rays focus, but now I want to exploit this generalized covariant entropy bound. I want to stop as soon as in fact, the best place to do it is right here. As soon as the light rays have crossed my object, now the object is completely contained on this partial light sheet. It's a light sheet where the area has not yet shrunk to 0. It's now this big, when originally it was that big. So there is some sort of annulus here, which is this area difference, delta A, or A minus A prime. Here's A prime, here's A. Okay. It's basically the amount by which the light rays have been bent to be, so there's an angle here that you can compute by literally the bending of light calculation, and which tells you what the width is. Okay, the angle, well, it's actually fairly easy. Just on dimensional grounds, the angle has to be m over r. This angle here has to be m over r. It's small if the object has very little self-gravity. Okay. And this distance here is r, because that's the closest I can bring to the screen to the object without missing parts of the object on the light sheet. Okay, so this width here is r times phi and is therefore equal to m. I'm working in Planck units. So m times g, if that makes you happier. And so this area difference, the area of this annulus here, well, it's that width times 2 pi r. So delta A is mr. Okay, and the entropy, the generalized covariant bound is precisely this statement. So we recover the Bekenstein bound. And if you follow things closely, you can see that again, you can see quite explicitly how G Newton drops out. So you can recover it if you start with this stronger starting point. The thing that has sort of been frustrating is, but first, are there any questions about this construction? Yeah. Yeah, you actually do get the 2 pi, yeah, if you do the calculation right. I don't attach particular significance to that, for reasons that I can explain now if you want.
Which R do you use when it's not a sphere?
Which dimension do you use? The thinnest one. So in that, yeah. Yeah, so you get something that's slightly stronger than the thing that Bekenstein advocated. But I never understood why he advocated the largest dimension. That didn't make any sense. Because also in his experiment, you could always orient the system so that the thinnest dimension is aligned with the radial direction. And that's what controls how close you can get the object to the horizon before you drop it in. So here as well, I mean, what you want to do is if it's not a sphere, you want to align the thing in such a way that your thinnest dimension is in the direction of the light rays. And then that's what enters here. So the 2r is really the width in the thinnest direction. Yeah, so the problem is this. And this goes back to all these arguments that Bekenstein and others have been having for decades about whether the Bekenstein bound is actually true. if you say, pick certain boundary conditions, like you take a spherical box or a rectangular box, you put certain boundary conditions on your field by hand on the mathematical walls of this box. And you compute the entropy that, how many quantum states can you have in this box up to a certain energy. Due to things like, for example, Casimir energies that can make the ground state have negative energy, you can have situations where, say, the entropy is 0, but the mass times radius is negative. Okay, and so clearly the Bekenstein bound is violated. And so then Bekenstein says, with some right, well, okay, but this is not very physical. Who gave you these boundary conditions that made sure that the fields vanish exactly on these surfaces that you just put mathematically into space-time? You have to build a wall there. And if you use the strong energy condition, you can show that the wall can only sustain the Casimir pressure if it's built out of materials that have enough mass to compensate for this Casimir energy. And it overcompensates by a huge amount. And so now the bound is fine, but what is the thing that it's actually a bound on? At which point do you stop? Strictly speaking, well, what do you want to say it is? It has to do with bound states. So you have to have a bound state in your theory. Well, if you have a bound state that's an energy eigenstate, then its radius is not well defined, and generally speaking, it will have exponential tails. The wave function will have exponential tails out to infinity. So what do you call the radius? What do you call the width of this system? Now, why do I worry about that here and not in the case of this bound in terms of area? I worry about it here and not there because when I write down S is less than A over 4 and I want to test that in a regime where semi-classical gravity is valid, I have to start by taking A to be very, very large. I don't want to take a Planck size sphere and then look inside that. I want to take a sphere that's big and then look inside that thing. So A is very large. So in order to try to violate this bound, I have to look at very large systems with a lot of degrees of freedom, with a lot of entropy. In that case, the thermodynamic description is usually accurate, and subtleties about exactly which quanta near the edge of the region I count and which I don't count because they actually have a little bit of extent across this mathematical boundary. Well, these questions are actually there, and they're perhaps bothersome at a formal level, but what I do doesn't affect the answer very much. It really doesn't matter, okay? Because all the numbers are large, and whether I count a few quanta near the edge or not doesn't make any difference. But here, consider the situation where I have a single but very long wavelength photon, a wave packet, okay? It has some characteristic scale, and it has an energy, so let's call that scale lambda, okay? It has that's going to be my R. So let's just call it R, sorry. Okay. Now, if it's a single quantum, it will have an energy of order h bar over R. Okay. So m times R is equal to h bar, and the right-hand side here is of order 1. The entropy of this single quantum, if it's a photon, is also of order 1. It can have this or that polarization. It has some handful of quantum states, perhaps. Okay. So I'm in a perfectly well-defined regime where I understand how to, gravity is not strong. I'm just doing quantum field theory, long wavelengths, arbitrarily long, so everything is totally under control. And yet I have a situation where both sides of the bound are order 1 and are comparable, and I would need to know exactly how to define the mass and the size of the system simultaneously in order to check if the bound is or is not satisfied. And so that's been an obstacle, at least in my mind, to making use of the Bekenstein bound or making sense of it. Yes?
Is there something that doesn't work quite so well for this stronger covariant bound difference variance?
And that's really the main thing, that in this, if you allow using this stronger bound, then that allows you to get into a regime where it becomes important to decide, entropy ultimately is not a completely local and sharp thing. And as long as the right-hand side of your entropy bound is really large, you will be testing the bound using systems where the non-locality of entropy is not very important. You'll know exactly what you mean by the entropy that you're going to put on the left-hand side. But once I allow you to tighten the bound in this way, then you can get systems that approximately saturate the bound and in which it then becomes important. In which it becomes important to know what the rules are. All right, so if there are no further questions, then let's continue tomorrow with a more cosmological direction.